Simple example. So here we have a function. Do I have a pointer? I guess not. Oh. No, that's a remote. Well, whatever. Here we have this hello function, which just prints the old hello world.
It's the blue disk.
Oh, very good. We have this function here, which simply prints hello world. And down here, we make a call to this little thing here. And this does everything. It exposes the function to Python, and you can just call it from right there in Python. It all just works. Well, maybe I'll come back to that. Give me a moment. You can wrap functions with arguments and return values just as simply, and they still just work. It's all nice and simple. Yes? An array of strings will become a Python list of strings. So it'll construct a new list and fill it with strings. So yes, there are more complicated return types. I'll get to even more complicated ones in a moment. We can do default arguments quite simply. And as you can see, these work just fine as well. Call it with one or two arguments. It all just works. And again, you still just call this same thing here. If you have an overloaded function, Python doesn't support function overloads. So you have to wrap it as two different functions, each with their own name. And then you call one or the other, and it's all very explicit. Python also has this thing called a Python object, which is this weird little class where you put in your argument. You make your arguments or your return value a Python object, and it'll just pass through whatever the Python object is. It overloads a whole bunch of operators, so you can write using a Python object like it's regular D code. And it all just works as if it were Python code. And you know that I'm concatenating two Python strings with the plus operator. It actually works. The concatenate operator works too. So it's just that Python uses plus to concatenate things. So that's all good. Exceptions work also. You have a D function which throws an exception. You call it with Python, and it throws this weird thing. You get back all the information about the exception. It was too wide for the page, but there it is. And everything is still just as simple as it ever was. If, going back to this add function we had above, if you try to do something with Python object which would cause a Python exception, it just stays the same old Python exception, and you get the original error. So everything is just simple. It all just works. This is good. Now take this struct. It's a struct. We got a function which returns one. We have a function which accepts one as an argument. The simplest way to handle that in this case is with this more complicated thing. So here we have a delegate literal which accepts the struct and returns an int. It just returns the struct's member. And then we have a delegate which accepts an int and returns the struct, and it just makes a new struct, sets the int to that, and returns it. And now, when we wrap these functions, you just call the one and it returns an int. You pass an int to the other, and it just converts it all to the struct behind the scenes. You can do this. You can return any type which Python knows how to convert, and you can have it accept any type which Python knows how to convert to wrap these, any arbitrary type that it doesn't know how to convert. And this can be useful. but sometimes you want to deal with a type more directly. Here's a class. So here's some new syntax. Wrap class. You pass it the class, and you pass it a member of the class, a method, and here we instantiate the class and call the method from Python, just like any other Python type. You're using your D type. Yes? It is different than the lowercase one. The lowercase one is a function template, and that one is a struct template, actually. It's a type. You're passing it as part of this big old tuple which gets passed to wrap class. For every member of the class, you would pass another specialization of def, and this is an API I worked out, which seemed the simplest way to pass all of these things to wrap class at compile time. And there are additional arguments to def, which are very much like the lowercase one. If you had overloaded member functions, you could specify their types, give them different names, and it would all work in Python. Because again, Python doesn't support function overloads. Once you've wrapped a class, you can use functions which accept it as a type and return instances of it. And it all just kind of works. So this seems fairly straightforward. I'm not sure how complicated this seems. To use it, it's very simple. That's the whole idea. Behind the scenes, it's doing quite a lot of very complicated stuff, but it all just works, which is the whole idea. Some more interesting things. Here's a simple function, which always returns the same instance of foo. And it turns out it always returns the same Python object, too. Objects keep their identity. This can be very useful in a number of situations. If you're using some idiom which relies on object identity or whatnot, maintaining this is very useful. And you wouldn't expect it to behave in any other way. We're getting into some more complicated stuff. Here we have a base class and a derived class, which inherits a method. We wrap the base class, tell it the method. We wrap the derived class, but we don't tell it the method. It gets it automatically. We make an instance of derived, and hey, we still have that method. It's all just there. It all just kind of works. You only have to tell it once in the inheritance hierarchy. Another interesting little fact. So we have a function which returns base, but it's actually returning an instance of the derived class. And in fact, the type that Python gets is of type derived. Python is dynamically typed rather than statically typed. This behavior is much more useful that you know what the actual type of the object is. It just does all the downcasting for you, basically. So there's a bit of runtime type information being used here. Just a bit of overload. We also automatically get the operator overload. So we have a class. It has an op-add. It returns an int. It just adds the int member of the two classes. We wrap the class, but we don't say anything about op-add. Python knows about op-add. That's a fairly standard function name, and so it can just do it. It just works. You don't have to specify it. This works for if you have a length property, it will wrap it so that you can use Python's built-in len function, which is the standard way of determining something's length. This does not work for toString because you might, the way D uses toString is a little different than how Python thinks of it, but you can explicitly tell it, here's a function which tells my class, here's a function which can represent my class as a string. This also incidentally means that if you're using Tango instead of Phobos, it won't assume you're using toString instead of toUTF-8. So that's kind of nice. I don't have a little snippet here for that. This is getting into a more complicated thing. We have a D-type base. It's the same one we wrapped above. And here we're subclassing it in Python. And we overload one of its methods. And look, that all just works. We make an instance of the subclass. We call the overloaded method. Very simple. This is what you'd expect to happen. Here we have a D function, accepting base, an instance of base, and we pass it this object we made here, the instance of the Python subclass. We pass it there, and it ends up calling the overloaded Python method. This is very useful. This allows you to expose your whole class hierarchy to Python. You even take advantage of all the mechanisms of subclassing, pass them back to D, where everything is handled quite neatly. And you don't have to specify anything in your D code. Again, well, it's farther up than I remember. Again, this is all we said to wrap it. We just told it about the class. We told it about its method. And we get all of this nice functionality for free. It's just kind of there. I was expecting more questions when I was talking about this because I've reached the bottom of my slides and had expected to go twice as long as I just did. Yes? Oh, you're right. I skipped that. This is how you build a module written in Py. Now, this is Python code you're looking at. And this would only look familiar to you if you've ever written C extensions to Python. Python has this thing called distutils, which in its regular form knows how to compile C in a way that Python can understand. Pyd comes with this module called celerity, which extends distutils and provides all the same stuff distutils does. Basically, you just tell it, here's my module, it's called foo. And you issue what is the standard way of building Python stuff, and it all just works. Yes?
In .NET languages like C#, there's a significant penalty at runtime for calling across the managed unmanaged boundary.
Okay.
I'm wondering, when you say you call from Python into D, is there any penalty regarding thread stop? Is there very much runtime code that happens when you make that call from Python into D?
There's very little. The overhead for calling from Python into C is quite low. Python is written in C, and so it's a native C API to it. And Pyd, in its simplest form, provides a great many templates which sort of generate all of the little wrappers between Python and your D functions. And all of that happens at compile time and is very fast at runtime. There is some overhead with regard to this thing. When you pass an instance of a class into Python, it has to look up in a hash table if it's already got a Python object holding a reference to that class. And so there is a hash lookup involved, which isn't that much of overhead, particularly compared to the overhead of just using Python in the first place. The thing with Pyd is it looks very simple from the outside, but there is a lot of interesting stuff going on the inside. This polymorphic call thing, in particular, there's a lot of trickery going on behind the scenes. It has to, but Pyd ends up pushing D's metaprogramming abilities to their limits. It does, and it's done so a number of times. I see Walter smiling about that in the back. And what it's doing here, I don't know. If you don't get why this is a big deal, you kind of have to just think about how you would, at runtime, almost overload a method of a class, and it's kind of a trick.
So
Yes?
it seems like you might not want that functionality sometimes. Because you could imagine a situation where you're going to let somebody extend your code and then by them being able to override your methods.
Then you could always declare your method as final. And then there's no way this thing could overload it. Then your decode would always call the final method, no matter how much Python overloads it. Python does not have the concept of final. You would overload it in Python, and your Python code would see the overloaded function. But if you pass it back to D, D would always see the original one, because D thinks of it as final. This is kind of weird behavior, maybe. But that's again, Python doesn't know anything about final. It's just not a concept in Python. There's almost no way to prevent it from being able to overload a method. There are some tricks to do it, but they're extremely hackish, and I haven't bothered to go into that. Yes? Deriving?
Yeah, the other way around.
Not really. What you could do if you wanted to do something like that, the trouble with Python classes is they are defined at runtime. They're completely runtime entities. And so what you could do, the simplest way to do something like that is going back up to this pied object thing. You could subclass pied object and overload its functionality somehow, and then sort of call back to the Python object inside of it when you want to call the superclass, basically. And that would work. That would be how you'd implement functionality like that.
I'd like you to get to the things that you can't do or that are very hard for you to do in ID, so that we know what kind of introspection features.
Right. Currently, one future direction, this business of overloaded functions, eventually I want to solve that, be able to actually wrap over a series of overloaded functions. And then depending on what Python type you pass to the function, it would pick the right overload, and it would all just work. There's some problems with that involved. For example, if you had one overload which accepts a short and one which accepts an int, the short version would never be called because Python doesn't have any shorts. And so that could be a problem. I'm not really sure it's much of a problem. Yes. Yes, you do have to explicitly specify the methods of a class. The traits feature, which was added in D 2.0, is a good start on that, but it's missing a few important parts. You can, using traits, you can get the names of every method of a class, but for instance, you can't get the static members of the class, and Py does have support for static member functions. I just haven't had an example of that in here. You can get the signatures of the overloads of virtual functions, but not of any other kind of function. And in particular, you can't get the signatures of the constructors from traits. And so these, and in fact, I also haven't really shown how you tell it about constructors. I had one back somewhere, which was it here? Well, it's in here somewhere. I'll look for it while I talk. Okay, maybe I can't do that. Pardon? Oh, right. There's an underscore in wrap class. I should know that. Oh, you're right. Uppercase init. That would be the thing. Oh, because there we are. Hooray. Okay. Here you basically give it a function pointer type with the types you pass to the constructor here and here. And there's sort of the same problem with this that you have with wrapping overloaded functions, which is you have to provide some way to, given a series of Python types, pick an appropriate overload. And so this has the limitation that you can't wrap two constructors which accept the same number of arguments, because the way it picks an overload is it just compares the number of arguments passed to it in a very naive fashion, which is also a limitation. And so if I solve the overloaded function problem, I solve that problem too. Yes?
How do you manage the reference copy? In which spots
Ah.
there are ways of doing that? There's two types of smart pointers. There's the borrow handle that doesn't bump up and down ref copy, and then there's the other kind. So do you map directly on the reference copy method?
The only place reference counting is an issue is with PyDobject. PyDobject is a very simple class. You pass it a PyObject star, or a raw Python object, to the constructor. There's an optional Boolean flag for whether it will steal ownership of the object, that is, whether it will increment the reference count. And then the destructor decrements the reference count. The destructor does. Sorry. This has the problem that the object's lifetime is managed by the garbage collector. And so if you just leave it to the garbage collector, the reference count will be decremented whenever, which can be a problem. If you explicitly manage the lifetime of the object with scope, that's less of a problem. If and when we get struct constructors and destructors, all of those problems will just go away. PyDobject will become a struct like that. Which will mean you wouldn't be able to subclass it, now that I think about it. Yeah, may have to have both. That's kind of, I hadn't considered that. But having the struct would be vastly preferable to letting the garbage collector just sort of do it. Yes? Yes, but you don't necessarily want to do that. For instance, here you are returning an instance of the class back to Python. I admit I haven't used scope classes that much. Right. Oh, I see. You make it a scope class and a non-scope class. You could do that, I suppose, but then you lose this nice simple thing here of just taking some PyObjects and returning one. Well, with the struct in this example, you'd just use the struct in all of these cases. And
I guess my point is that when you were hoping to use a struct, constructor, and destructor, what you could still do with the PyObject is just the scope class, I think.
One of the major uses of PyObject is for use as function arguments and a return type. I mean, this function right here is one of the primary uses of it. Being able to simply take any Python object, do stuff with it, and return something back. And there is a convenience function in Pyd, which is just called py, which takes, it's just a function template, takes any D, anything, and returns a Python object, which represents it. It's the same functionality that actually is used when you return anything from a function. And I forget where I was going with that. But in any case, using a scope class does have those limitations of passing it in and out of a function, and that, I don't know, that would lose some functionality that you would still have with struct thing. Yes?
So you mentioned that Python exceptions would be passed through properly and received in Python
Yes.
properly.
You can catch them. They are an exception type.
Deal with them as the specific exception type.
Currently, all Python exceptions they're handled by being thrown as a D exception called Python exception, and then they're cut by Python and re-raised as the original Python exception.
What I mean is, if you catch just a Python exception,
Right.
can you say, what are you really in Python?
Currently, you can extract from the Python exception the Python objects representing the exception, but you're doing that with the native C API. You have to, if you're going into that level, you have to fall back on the C API to deal with that, which you can do. Yes.
Now, Python, as I understand, has some garbage collector.
Python is reference counted.
Oh, it's reference.
Python is reference counted with a mark and sweep collector for backup in the event of circular references.
Have you encountered any sorts of problems, I guess, between the garbage collector and Python garbage collector?
Yes, that's actually a very interesting problem. I've already talked about with PyObject, when you pass a Python object into D, how you handle that, and it's the kind of wishy-washy thing here of letting the garbage collector decrement the reference count. When you pass a D object into Python, it's a little more interesting. When you return a class instance to Python, here we are. So func2 here returns an instance of foo. That gets wrapped with a Python object, which holds on to it, and the Python object lives off in Python's memory. So a reference to that instance has to be kept by Py. It has a big old hash table where it does this. It's the same hash table I mentioned earlier. And this hash table keeps the garbage collector from collecting it. When the Python object is collected by Python, its destructor removes that reference from the hash table, and the dgarbage collector will collect the object then whenever it gets around to it. This is actually a fairly difficult problem because there's more than one way to keep a reference to a D object. You can have a regular class reference, but you can also have a reference to a class object in a delegate, for example, if you have a delegate to a member function, and you can return delegates to Python, and they'll just become a callable Python object. It's a nifty feature I should have covered here. And you have to then be able to keep multiple kinds of delegates to the same object and be very smart about it. Because even though it keeps identity, it always has the same Python object for a given D object, you can still have multiple references to a single D object. Delegates and class references and arrays if I ever get around to doing them properly, which that's another weakness right now. Arrays are also tricky. Because it's a weakness of Py. What I have to do to support arrays properly is write a new Python type, which specifically wraps a D array, which it's kind of tricky because of the way the reference keeping work and slicing allows you to do some strange things. You can have multiple array references, which are different references to the same object, and they're the same type, and so the way this keeps references, it only checks based on the type of the reference. So it. Well, remember, C++ is not garbage collected. This reference keeping relies entirely on the garbage collector. So when you're talking about Boost Python, you have to. A lot of Boost Python's API is about explicitly telling it what the ownership semantics of the object are, and when it should be destructed, whether the Python object should delete it when the Python object is destructed, or whether it's more of a weak reference or whatever. Whereas this simply, hey, it's garbage collected. Let's rely on that, which I'm sure Chris wouldn't like very much, just relying on the garbage collector like that. This thing thrashes the GC so hard, you can't imagine.
You're using an interpreted language anyway.
Right. If you're using that overhead, good luck. And if you really wanted to, you could wrap the garbage collector's collect function to Python and allow Python to just keep calling it, but that's kind of an iffy solution. So being able to use slices from Python would be great, but I'm not quite there yet. At the moment, whenever you return a D array to Python, it creates a Python list, which is the native Python type, and copies in the array contents, and it's kind of slow and not the most optimal solution. It does the same thing with associative arrays, too. It creates a Python dictionary and copies in all the elements, also kind of slow and non-optimal. But yes?
This might be a little bit out there, but referring to Sean's presentation yesterday on overloading garbage collectors, would it be possible or worth it or more efficient to have a way to overload D's garbage or to replace D's garbage collector and use Python, or is Python even powerful enough?
When you...
Not now. Would that be a hypothetical?
Well, I never thought of doing that before.
I happen to guess that you're entering strongly into undefined territory.
Yes. When you...
Or perhaps the opposite. It would be, yeah, because Python's garbage collector is probably limited just by the fact that
The opposite is essentially impossible because Python is primarily reference counted. And furthermore, this is written with an eye to extending Python with D rather than embedding Python inside of D. And so changing how Python manages memory with this is not possible. But whereas having D use Python's memory management stuff could be interesting, but again, Python is primarily reference counted, and that wouldn't really work. Using Python's actual garbage collector to do that, I'm not sure that's such a wise idea either, because again, Python's garbage collector is its backup memory management system, and not the primary one, and I don't think relying on it would be good. Yes?
You've written this presumably for the ability to do something with it. Have you done anything interesting with it?
No, not really. And the reason is it's continually unfinished. There are all these weird little corners. I've mentioned a few of them, and so I've been kept quite busy working on those. Yes. Aha. Yes.
You said arrays and associative arrays turn into lists and dictionaries. Do those carry closer to reference semantics or value semantics? Meaning, if you pass in a slice to I, and then you change the object, do those changes reflect?
If you say you have an array of class references in D, and you return that to Python, you'll end up with a list of objects. And then if you mutate those objects, the objects from D will mutate too. But if you swap out a new item into the list, that won't get reflected back to D because the list is a completely different object from the array. If I created, which I want to do eventually, a dedicated Python type for directly wrapping D arrays, that behavior would change. And in fact, they'd become type safe. If you tried to put an item in there which couldn't be turned into the type of the array, it would throw an exception and barf. Yes?
So this is for putting D into Python, not Python into D?
This is primarily for putting D into Python. The use case I have in mind, which is the same use case you typically use the C API in Python for, which is you write your Python code. Python is very easy to prototype with. It's very easy to get applications up and running very quickly, but it's not a very fast language, and so you fall back on a systems language for speed. And that's primarily what this is for. You write your D code just like regular D code, and then you just do this little thing, and all of a sudden it's there in Python. That's the primary use case for this. For embedding Python in D, this does provide a lot of convenience functions for just turning D stuff into Python stuff and vice versa. It provides some other convenience functions like a nifty function template where you pass it a bunch of D stuff and it returns a Python tuple, which is very useful in a number of contexts in the Python API. But if you're going to be doing that, you will end up just using the C API directly for doing that. This does not provide a lot of support for simplifying that.
Second question, when you're building an extension,
Yes.
so it basically just piles that foo.d to some library?
Well, I can show you. It's a little small. Here's a command line. So I have, this is completely unreadable. But, yeah, I could change the font. I'll change the font, which is also hard to read. That didn't help. Yeah, we got to make it bigger. Okay, we'll call it that much bigger. That's a lot bigger. Yeah. I'm not sure this is that smart. Okay. That's kind of readable. Oh, there was a checkbox for bold? I didn't see that. Ah, so there is. Maybe? Okay. So here we have that hello world module I showed you earlier. Same thing. And we have that pretty much that same setup.py that I showed you, which, again, this is very standard if you ever have used distutils. If you've ever compiled C extensions for Python, this is the standard way of doing it. And then you just type in python setup.py build, assuming I typed that right. Very good. Oh, yes, I'm missing a letter. Okay, and then you hit enter, and a bunch of stuff flies down the screen. And then it's built. So that's building it. You can now, I have a little module here which...
So what is built? A library?
It is a DLL, basically. It is actually a .pyd file, which actually has nothing to do with my library. That's the standard name for Python extensions, which are DLLs. If you were to build this on Linux, it would be a .so. Which,
for every extension you add to Python, you get another garbage collector.
right, and yes, that is true. And I'm not sure exactly. Right. Right. And what was I about to say? Oh, yes. I didn't remember. And each of those DLLs or SOs will, Python just imports those directly as a Python module. This is all the standard C API stuff. If I have a little test module here which will import and run hello world. That little pause, I think, was Python starting up. And I mean, that's what hello world module did. Yes?
Is there a way to get it to use the build system for larger APIs and such?
I've been looking at getting it to build with DSSS. This is kind of tricky for a couple of reasons. Primarily, to build an extension module like this, PyD is more than just a library. It also has to know the name of the extension at compile time. It has to generate a little tiny bit of code to do that. And DSSS has no simple way to call back to the library you're building, to the thing you're building from the library Not to impugn Gregor's good work, but
Python extensions, you would expect this as a file.
you would, pardon?
You would expect a set up Py file like this.
You would. This is, again, the standard way of doing it. But I do want to get it working with DSSS. And also, if I got it working with DSSS, I could set it up so you could build, you could embed Python using it as well. That would be simpler. This distutils thing is very geared toward building extensions, not embedding Python. If you want to embed it, you'll also have to do the build stuff manually, which is kind of complicated. You have to pass in just the right version flags and link in the right things, and it's tricky, which is, I guess, is what Gregor is trying to solve. So that is tricky. Yes?
What would it take to be able to just throw a module at Pi?
Aha.
To just do everything.
This,
Public imports, everything public in that module, everything.
it would take a parser and a code generator. And this could be done. Would not be that hard because D is quite good at that sort of thing. I've just shied away from it because of the simple philosophy of avoiding code generation whenever it's possible and just using the language. Aside from the little tiny bit of code generation that Py does, which involves just creating a single function with a particular name that has the module's name in it, the whole thing is just a big old template library. Yes?
Goes back to something, right now, using loose Python, the best way to write a module is using Python++, which is Python bindings that generate loose Python. It's not so much that loose Python or Py doesn't aren't easy to write. It's just that
For large projects, they're hard. There's a lot to write, right?
Python++ being in Python, you can concatenate strings and do all kinds of money
Right.
you normally want to do. Basically,
And it would be not that hard to write something which does that for Py.
it can actually probably end up being better for D because the way Py++ works is it uses GCC XML.
Right. And
GCC XML works for Python loose Python because it doesn't understand definitions, but it understands all the declarations, and
that's all you need.
But since writing a D parser isn't that complicated, that's all. Yeah.
Or you could repurpose the DMD front end to do that. There are any number of options.
Right. So I think ultimately, in the long run, that model is a good one because it's a lot easier to write your module generation in Python itself than it is writing anything else. So
Right. Because
put that as a direction to go
For-
not necessarily for your work, but for
right, for really large classes that can get cumbersome. There are also currently some symbol length issues. If you wrap a class which has a large number of methods, you will very quickly run into the symbol length issues because that is a tuple right there where you're passing all the methods. And there are a couple places where it has to include that tuple 3 times in the name of the symbol, which can get you into some real trouble very quickly. Yes? When I started writing Py, CTFE didn't exist yet, and so most of the code base wouldn't do anything with it, and also not really, because a lot of what Py is doing, when you're exposing stuff to Python, you're writing a whole bunch of, if you were to do it manually, you'd be writing a whole bunch of tiny little extern C functions, for each method, for each function, whatever. If you were actually writing it in C, those would be your functions. You wouldn't be delegating off to the actual implementation usually. But what Py does then is, instead of writing one little extern C function for each method of a class, there is a single extern C function inside of a template which can generate the right thing given a class and an alias to a member function. And CTFE couldn't really, that it's a different problem. It wouldn't really apply for most of what Py does. Yes.
For the big classes and whatnot, big projects that don't quite run into simple language, what are your compile times?
Well, I just compiled one here. I will compile what's basically my unit test, which hopefully works. Well, here, we may have to touch it to get it to work. Okay, so here's my unit test, which is somewhat larger than Hello World. And I can't type looking back and not looking, and okay. Yeah, Pytho. Yes, I'm not a very good typist, I admit it. Okay, and here's my unit test. Boom, it's done. Didn't take any longer. This is because DMD is extraordinarily fast, and it's a wonderful thing. Whereas, yes, Boost Python, there are stories of multi-hour compile times with Boost Python, even on modern machines. So this, I think, is a good selling point for Pied. That you... Not very. I don't have a very comprehensive unit test thing. That was it just there. And yes, you can rep structs. You can see it in the unit test there. You pass in the name of the member as a string, and it uses string mixins, which I find very ugly, but that's how it works. And structs are kind of weird. I'll just go off a bit and mention this. When you return a struct by value to Python, it will it will create a new one on the heap, copy it into that, and the Python object will pass around a pointer into that, which is kind of weird, but Python has very strict reference semantics. There is no such thing as value semantics in Python, and there's no other sensible way to handle structs in Python. If you return a pointer to a struct back to Python, it will actually it will actually just store that exact same pointer. If I remember right, I'd actually have to go back and look at that again. And so it'll be just it'll act as another reference to that same struct, which might be the wrong thing to do if you don't want it to keep an actual reference to a returned pointer, but that's kind of weird. Also, when you wrap a struct like that, you'll automatically be able to handle both the struct and pointers to that struct. Maybe I should have had some actual examples to clarify what I'm talking about. Did you have a question, Gregor? Oh, very good. What else do I have in my unit test? You can see up here a very long list of defs when I was finding out exactly how many things I could cram in before the symbol length blew up. As you can see, it's that many before the comment. So that's about how big of a class you can wrap with Pied before it goes all crazy and you get some incredible errors. The Python module C-type? C-types, of course, expects to work with C. And there might be some issues getting that to work with the D ABI, and I haven't even thought of trying to use C-types with D. So.
Was there a section for free functions?
Yeah, free. That was the very first thing I covered, in fact. Here.
So they're easy.
They're easy.
So
They're
combining the changes in D2 to be able to call member functions and free functions identically. Syntax.
Right.
Syntax change means you'll be able to include a whole bunch of free functions a lot easier without needing a symbol component. You'll have typically fewer class member functions.
Yeah. You'd be able to factor out the member functions of the class to free functions. Python does not have the exact syntax that was proposed where you factor out the first argument in front of the dot.
They won't be as easy to call.
So you'll have to call it explicitly with the thing as the first argument, but you could wrap the functions just fine, and that's fine. Yes. Yes, if introspection got to the degree where I could see all of the declarations in a module. Right. Right. If that got in the language, then you could just say module init and pass in the name of your module or something, and it would just work. Right. And some of the reflection stuff which already exists for D gives you the reflection info at a runtime, which is not good enough for PIDE. To implement this polymorphic insanity, you have to have all of the information about the class at compile time for it to generate all of the necessary stuff. And so runtime reflection is not sufficient to do that. And this is also why I have been asked before, why do it all with templates? Why not just do this at runtime? And the reason, in part, is because you can't do this at runtime. Yes?
If at compile time you had access to the full parse tree.
To the parse tree?
Yeah, parse tree.
Maybe that would involve.
I think it would be completely insane.
It would be completely insane.
Compile time,
You'd have.
Function that you would do an import this file.
If I had access to the parse tree at compile time, that would certainly be very powerful. I'll say that for it. But that could be very difficult to get right, probably. I don't know. Without seeing exactly how you'd use that, it would give me all the necessary information, no doubt. I'd rather just have the built-in trait stuff that's been talked about, which is much more direct and simple to use. Yes, Walter.
Parse tree would be a whole lot of good, because
Oh.
parse tree would be before semantic analysis.
True.
You want it after semantic analysis.
Okay, that is true. You're right.
Otherwise, you have to build all the logic of the compiler.
Or let someone else do it and import their library that does that. That's what I did. Where is Don? I've used his name of module in PIDE for quite a while. That's how I derived the names of things, just from their symbol. Although I think I've replaced a little of that functionality after we got string of, but it's all the same basic idea. So yeah, a lot of those kind of little information retrieval things. Some of them are easier to do than others. But yeah, okay. So a parse tree would be more complicated. Okay. Well, that was actually an hour, it looks like. Or was it? Was that half an hour or an hour? Wow. Okay.
So we'll take about a 15-minute break or so.
Okay.